Lewis electron dot structures and resonance. This is kind of a curious phenomenon. When you can draw more than one Lewis dot structure for a molecule, that's actually a good thing. And this molecule actually bounces around from one structure to the other. None of them are actually correct. It's kind of a mixture of them all. So that really helps lower the energy and makes the structure much more stable, making it a better predictor of just what that molecule can and cannot do, both chemically and physically. This is a good example. Which oxygen atom should carbon form a double bond with? Symmetrically, it really doesn't matter. It could form a double bond here, here, or here. Wherever you move that double bond to, it works. So where is the double bond? It's really a combination of all three structures. Not one of them is the correct one. It's a combination of all three, all happening at the same time. That's what really helps make this molecule stable and at a lower energy. So let's try writing Lewis structure for the carbonate ion. So carbon has to be in the center, surrounded by 3 oxygen. We've got 4 valence for carbon, 3 times 6 for oxygen, 2 extra for the charge. So that means 24 valence electrons total. So if I make octets around all the surrounding atoms, and anything left over, put on the center atom. Now I have 8 on each oxygen. There aren't any electrons left, so nothing to put on the central atom, leaving carbon without an octet. But remember CNOS, so I can get carbon's octet just by making a double bond. So let's move this one in there. So my answer would be this. Here's my double bond. Now carbon has an octet. Oh, don't forget about my charge, right? This has to be a -2 charge overall. However, instead of that pair of electrons, I could have used this one, or I could have used that one. There's actually 3 resonant structures. Let's go ahead and draw them. So in the second structure, I'll make that double bond. Third structure, I'll make that double bond. There's my second structure. My third structure, a double bond at the bottom oxygen. And don't forget my brackets for the -2 charge. Now to show that these are resonance structures, you draw arrows in between the structures. To show that the true Lewis dot structure is actually a mixture of all 3. So let's try the same thing with nitric acid. Write resonance descriptions for the following. Nitric acid. Probably should have gave you the skeletal structure for this molecule, because acidic hydrogens are always bonded to an oxygen. Let's find our valence total. 1 plus 5 for nitrogen plus 3 times 6 for oxygen. My total is 24 valence electrons. So let's first make bonds for everything. Octets on the surrounding atoms. Anything left over, put on the center atom. Okay, how many we used up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up all 24. Okay, it looks great. I just don't have an octet on the nitrogen. So how do I get an octet on the nitrogen? Okay, so with CNOS, I can make double bonds here. Let's move an oxygen into here. So there's one structure. Here's another structure. And there's a third. Here's a third way to get that octet on the nitrogen. So there's actually 3 different ways. So let's try this. Let's try the green one first. So there's one structure. Now let's try the other one. Now let's try the purple one. Move those lone pairs, see how it works. There's another structure, and our third structure. Okay, now there's one thing that's wrong with this answer. Can you see what it is? Through symmetry, these two are resonance structures because they look exactly the same. This one is different. So it's not a resonance structure. Why is it different? Because look where the double bond is between this oxygen with the hydrogen on it. That's a shorter bond. It's way too short. Here it's a single bond and a single bond. So we cannot include this in our resonance description. It's only these two. Let's try sulfur trioxide. We have 6 plus 3 times 6, 24 valence electrons. So we connect them, make octets on the surrounding. So sulfur does not have an octet, but that's an easy fix. Let's just move the lone pair in. Now we can do that with each of the surrounding oxygens because they're all identical. So we can draw 3 structures. And one more. Now the double bond over here. So there's our resonance descriptions for sulfur trioxide. Use resonance to describe the electron structure of nitromethane, and they give us the skeleton structure. Let's find out the total first. We've got 4 for carbon, 3 for 3 hydrogens, 5 for nitrogen, and 2 times 6 for the oxygens, for a total of 24 valence electrons. So how's this going to look? Well, let's just use our structure here. Let's connect everything, make octets on the surrounding atoms. How many electrons have I used up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we better erase this. So now we have 24 electrons on our structure. Nitrogen does not have an octet. Carbon is happy. So we have 2 possibilities here. There's one, and there's the other one. Draw those 2 resonance structures with an arrow in between, and we're done. Now let's put in the electrons. Double bond with this one first. Now let's make a double bond with the other oxygen. And there's our answer. The resonance description of nitromethane. Write Lewis formulas for the following. Xenon difluoride. Xenon is a noble gas, so that's 8 electrons. I have 2 fluorines, so 2 times 7. My total is 22 valence electrons. So xenon has to be in the center, surrounded by 2 fluorines. First thing I'll do is connect them. Make octets on the surrounding atoms. And anything left over, put on the center atom. So I've got 8 and 8 is 16. I have 6 electrons left. So let's put them all on that center atom. Now it doesn't look right, but xenon just simply is not following the octet rule. What can you do? We're done. Xenon pentafluoride, cation. 8 for xenon, 5 times 7 for the fluorine. Subtract 1 for the charge. I'll have 42 valence electrons to work with. 5 fluorines surrounding this xenon. So let's connect them. Bonds. Let's make octets on all the surrounding atoms. And again, anything left over, we'll put on the center atom. Okay, each fluorine has 8. I have 5 fluorines, so that's 40. I have 2 left over. Xenon definitely is not following the octet rule. The whole molecule has a positive charge. So try these and see if you get the same answer that I get. Triiodide. 3 times 7 and an extra charge makes it 22 valence electrons. So I have iodine in the center, surrounded by other iodines. Make octets on the surrounding atoms. Anything left over, put on the center atom. 8 and 8 is 16. I have 6 left. 2, 4, 6. And the entire molecule has a -1 charge. Iodine tetrafluoride. 7 plus 4 times 7 and an extra charge. I'll have 36 valence electrons to work with. So I have iodine surrounded by 4 fluorines. Connect them. Bonds. Octets on all the surrounding atoms. And if I have anything left over, it goes to the center atom. Each fluorine has 8. I have 4 fluorines, so 4 times 8 is 32. I have 4 extra electrons to put on here. There they go. The entire thing has a charge of a -1. So iodine definitely is not following the octet rule. Boron trichloride. Boron is in group 3. I have 3 chlorines, each one has 7. It's 24 valence electrons to work with. So boron has to be in the center, surrounded by 3 chlorines. So we'll first connect them, make octets on the surrounding atoms, and if anything is left over, we'll put it on the center atom, just like before. 3 chlorines, each one has 8. 3 times 8 is 24. Hey, I'm done. You would like to make a double bond with the boron, but you can't because CNOS. It's not in there. So you just have to leave it like this. Boron is happy. That's our answer. Now we're going to find a better way of doing this the next class period. It seems kind of random and hunky-dory, but we'll have a rule called the formal charge rule that will really help us to determine these things. Beryllium dibromide. Beryllium has 2 valence electrons. Each bromine has 7. That's 16 valence electrons total. So put beryllium in the center, surrounded by 2 bromine atoms. First thing we do is make our covalent bonds. Surround the surrounding atoms with octets. Count them up. If we have anything left over, goes to the center atom. 8 and 8 is 16. Beryllium is not a member of CNOS, so we're done. Beryllium just is not obeying the octet rule. Again, the next class period will help us to really determine these things a lot better by providing us an additional rule called the formal charge rule. But the main idea here in writing Lewis dot structures for molecules is the first atom always goes in the center, surround that center atom with its surrounding atoms, make octets on all those surrounding atoms. If you have anything left over, put it on the center atom. If you don't have enough electrons for that center atom to have an octet, make double bonds or triple bonds. It just has to be a member of CNOS. Carbon, nitrogen, oxygen, and sulfur are the ones that allow us to make double and triple bonds. Good luck.